Hello everyone. Here we're going to be talking about repeated interactions. So in this chapter, we've been thinking quite deeply around this question of externalities or external costs that players impose on each other in coordination games or social dilemmas. So here we have to think about situations in which Abdul and Bridget, they both impose an external cost on each other when they're engaging in fishing activity. Okay, and so this external cost, it's something that captures the fact that when one player fishes more, the other player catches fewer fish. And that is true for both of them. So then, when we're thinking about repeated interactions, we can think about changing the rules of the game such that players internalize external costs by repeating the game for many periods. So instead of just saying that this is a one-shot game where they're only interacting for one period in the lake that they're fishing in, we think about them doing this over several periods. Okay, so strategies as a result can now be conditional on what the other player has done in previous rounds of play. So if one player has fished less in a previous round, that could affect how that would be interpreted by the other player for the next round of play. Similarly, if the other player has fished a lot in one round, that could affect how the other player thinks about what they should do in the next round of play. So one example of this is what we call a tit-for-tat strategy, or a nice tit-for-tat strategy. A nice tit-for-tat strategy is the following in this context. Play the strategy that would implement the social optimum, which is fishing 10 hours, in the first round, and on the next round and successive rounds of the game, play whatever the other player played on the previous round. So imagine that Abdul and Bridget are playing this game for the first time. Abdul is playing a nice tit-for-tat strategy. When we think about this, what do we think? We think that he is going to start off playing fishing 10 hours. Then if Bridget in that same round of the game plays fish 10 hours, in the next round, Abdul will play fish 10 hours. If in that next round, Bridget also plays fish 10 hours, then in the following round, Abdul will play fish 10 hours. If, on the other hand, Abdul had started off playing fish 10 hours and Bridget had started off with then fish 12 hours or more, then with that Bridget doing that fish 12 hours, Abdul in the next round would say fish 12 hours. Then if Bridget again fished 12 hours, Abdul in the next round would also fish 12 hours. Now, here's the thing. If Bridget changed her activity, then what this means is that Abdul would basically forgive her and return to fishing 10 hours if Bridget had fished 10 hours in a prior round. Okay, so that's why we say we have a nice tit-for-tat strategy there, a conditional strategy that is based on what one player does in a previous round. Okay, now if we think about the two strategies here with fishing 10 hours and fishing 12 hours and with the parameters that we have in the game from this chapter with alpha and beta, then we end up with the following payoffs in this 2x2 payoff table. Okay, so then the question is, what is the solution to this game and what kind of game does this resemble? So we've basically taken the continuous strategies of fishing HA for Abdul and HB for Bridget. We've taken the numbers, substituted them into the utility functions, and then we've said, what is going to happen if they fish 10 hours or fish 12 hours? And so we can see here that we've got payoffs of 150, 156, 140, and 144. So with those payoffs, we can think about how we'd find a best response. So if we are doing this as usual, and we're thinking about Abdul's payoffs are in the bottom corner of each cell, and we can compare 150 and 156, and we can see that for him, 156 is a best response, and so we put a solid circle there. Then we compare 140 and 144 against Bridget playing 12 hours and Abdul choosing 10 hours or 12 hours. And we can see that once more 144 is greater than 140. And so Abdul's best response is to play 12 hours. So Abdul has a strictly dominant strategy to play 12 hours. Then if we think about Bridget, what does she have? She can fish 12 hours or 10 hours against Abdul playing 10 hours. Her payoffs are in the top corner and in red. And so with 156 versus 150, she prefers 156, and we put a hollow circle there for her as her best response. Similarly, for 12 hours or 10 hours versus 12 hours by Abdul, she can get 140 or 144. So 140 or 144. What does she prefer? 144 is greater. And what do we have there? We have a mutual best response at them both fishing 12 hours. And so they both have a strictly dominant strategy. to fish 12 hours. So there's a 2x2 version of the game from our payoff functions. Now here's the thing. What kind of game does this look like? It looks like a prisoner's dilemma game. We have the payoffs that the players receive, 144 and 144. That outcome is not Pareto efficient. In fact, 150, 150 up here, we can see there the players can both get higher payoffs. So fishing 10 hours is Pareto superior to fishing 12 hours. 150, 150, where they're both fishing for 10 hours, that's also Pareto efficient in comparison to 144, 144, or fishing 12 hours by both of them, which is Pareto inefficient. This game is a Nash equilibrium. It's a social dilemma, as we've been thinking about throughout this chapter. Now, when we're trying to think about this game and trying to kind of unpack this a little bit and thinking about this idea of a prisoner's dilemma, both players adopt dominant strategies. So the Nash equilibrium is also a dominant strategy equilibrium, as we've seen before. Now, so what we want to understand is how will introducing repeated interactions change the outcome. So this is the same thing that we've done previously. We've labeled them A, B, C, and D, and you'll see that in the textbook we refer to those different cells just by those different labels, as it helps us to understand what might happen in the repeated game. But what I want you to think about for the moment are these different payoffs: 150, 140, 156, and 144. And so what we're going to say here is that imagine that for each round of the game, there's a possibility of the game repeating. Okay, there's a possibility that they're going to interact again. And that probability could be, for example, 90%. Now, as we did in previous chapters, what we can do when we think about that is that if there's a 90% chance of the game repeating each round, then in expectations, we think that the game is going to last about 10 rounds. Okay, so we can do that by thinking about how probabilities work and how series work. And you can think about that and you can check the mathematics appendix if you want to understand the mathematics behind that. But the basic intuition here is if there's a 90% chance of us repeating the game each period, then the game should last 10 periods in expectations. Okay, so what do we do here? We're going to think about the stage game. So this game over here that we've seen previously, we call that the stage game. And it's a stage game because it's a game that happens at each stage of the interaction. Okay, so we take that stage game and we repeat it every round. Now, there are two potential strategies in this kind of overarching game. The two strategies are going to be just defect. And so what defect means is you're simply going to play the 12 hours strategy in each stage game. That's the same as defecting or not cooperating. And cooperating would be fishing 10 hours. Okay, so we're going to look at two different strategies here. Like I said, the first one is just defect. Just play 12 hours. Play the stage game Nash equilibrium every single time. Now, another kind of strategy is what we're going to call a conditional strategy. And a conditional strategy is one which is based on what another player has done in a previous round. Now, unlike the more forgiving tit-for-tat strategy, the one we're talking about here is what we call a grim trigger strategy. And it's grim because if your opponent cheats even once, you're basically going to cheat the rest of the game yourself. Or if your opponent defects once, you defect the rest of the game. It's not at all a forgiving trigger strategy or conditional strategy. So what it means is you're going to start off cooperating. You're starting off playing the cooperative social optimum strategy of fishing 10 hours. But then if your opponent ever defects, you defect for the rest of the game. That's what grim trigger does. Okay. Now, what are we going to do? We're going to take these and we're going to calculate what they're going to look like for a 10 round game based on these probabilities that we mentioned. Okay. So the first one is defect. If I am playing defect and you're playing defect, we get 144 each round. So that's this outcome labeled C. I get that and you get that for every single round of the game. There are 10 rounds, therefore, or 10 periods. Therefore, we take 144, we multiply it by 10, and we get 1,440. Okay, that's easy. Now, if I'm playing grim trigger versus grim trigger, what does that mean? It means that I'm playing cooperate and you're playing cooperate. We both get 150 in each round of the game, this outcome labeled A. And with both of us getting 150 each round, and us both cooperating, neither of us ever defecting, we end up with payoffs of 1500 in the 10-round game. Then we get the two more complicated ones. If I am playing Grim Trigger and you're playing Defect, in period 1, the Grim Trigger player receives 140. Then he defects on all subsequent rounds. And so the probability that the second one happens is P, which we said was 90%. And so therefore the game is likely to continue in totality for 10 rounds. And so you're going to end up with 144 times 9 rounds, plus 140 which you received in the first round. And therefore your total payoff is 1,436. So 140 in the first round plus 9 times 144. Okay, so that total 10-round game. Okay, so that's 1,436. All right, now the next thing that we want to think about is defect versus Grim Trigger. So if you're on the other side of that equation, you've defected, the other person's played Grim Trigger. In the first round, you got the high payoff of when you defect and they're cooperating. So you're getting the 156 in the first round. But then every subsequent period, what you get 144. As a result, your total payoff is 1,452. Now you can see the direction in which we're going here. We've got 4 different payoffs, 1440, 1500, 1436, and 1452. We've got 2 potential strategies, Grim Trigger and Defect. What does that mean? We can put them all into a game table. Okay, so with this potential for the game being repeated as 0.9, and with our ability to sum up the different payoffs like we just did, we can see that we've got payoffs of 1500, 1500, 1452, 1436, 1436, 1452, 1440, 1440. Okay, the question is, what is the Nash equilibrium of this game, and what kind of game is it? So let's think about that for a second and look at Abdul. Abdul compares Grim Trigger versus Defect against Bridget playing Grim Trigger. He can get 1500 versus 1452. He prefers 1500, so he's going to put his little circle in there. For Defect or Grim Trigger against Defect, he can get 1436 or 1440. 1440 gets him a higher payoff. He's going to put his circle in there. Now, what is Bridget going to do? She's going to go through a similar process. 1500 or 1452 against Abdul playing Grim Trigger. What does she prefers? She prefers Grim Trigger. She's going to put her hollow circle in there. Similarly, Defect or Grim Trigger versus Abdul playing Defect. She gets 1440 or 1436. 1440 is larger. She puts her hollow circle in there. So there are 2 Nash equilibria in this game. The one Nash equilibrium is Grim Trigger, Grim Trigger. The other Nash equilibrium is Defect, Defect. Now with this, we've also got 2 Nash equilibria, and one of them is Pareto superior to the other one. So Grim Trigger, where they're both getting payoffs of 1500, that's Pareto superior to Defect, Defect, where they get 1440 and 1440. So this one being Pareto superior means that we have an assurance game. So as a reminder, what do we see? We've got these 2 Nash equilibria, Defect, Defect, and Grim, Grim. The Grim, Grim one is the one which is socially optimal, and it's an assurance game like the Planting and Palanpur game. And you'll recall from Chapter 1 and Chapter 2, when we spoke about these kinds of games, assurance games, these kinds of games make it easier to get to the Pareto superior and Pareto efficient Nash equilibrium rather than the Pareto inefficient defect equilibrium, because the players could choose to obtain this one. Now, what we could also do is we could apply a method from Chapter 2 and also try to find the expected payoffs for these players with these 2 different strategies, and also identify the risk dominant strategy. I leave that to do as an exercise for yourself if you're interested. But for the moment, the point is that we can see that by internalizing the externality through repeating the game over multiple rounds, through adopting a trigger strategy or a conditional strategy, which is a strategy based on what another player has done in a previous round, you can obtain a better outcome from the game. And that's the basic intuition of repeated games, and how repeated games can help us to deal with problems of external costs and the lack of internalizing that externality in the stage game or a one-shot game.